All right, part two. Two. That'll do. Yeah, of this Sean Carroll video by this Robinson Erhardt guy. So he interviews a lot of, some of it's philosophy and some of it's physics. So it's a kind of the same mix as Joe Rogan in a lot of ways. So in a lot of ways, it's a parallel podcast. But anyway, um, it's physics. Interesting subject, but all they talk about is woo, and they don't get to any of these, the basic elemental physics, energy conservation, conservation of motion, But anyway, yeah, so I don't think I have to say much else, and we could probably just get on with it. All right, so he's starting with something. He's answering some question. He's going to say, I think both physicists and philosophers, like there's some kind of philosophy of physics, which is kind of silly, or even philosophy of science, when no, there's just very good arguments and really crappy ones. There's logic. There you compile facts and you present facts. I'll keep saying this is a trial. A trial is like one of these perfect things that human beings came up with as an idea, where you have this theater for the argument and you present all of the evidence and you pick at it and prove it by showing one side to have more evidence. And in some cases you need to have a real proof, in the sense that you have to establish it as, okay, we're for sure this time, beyond reasonable, foreseeable error. And none of their physics is beyond reasonable and clearly foreseeable error. It's really weak evidence, and that's all. That's only fair characterization. Very weak circumstantial evidence, no hard good evidence.
Philosophers have a huge role to play here. I mean, philosophers have certainly kept alive these set of questions, and they've helped us understand why some.
So again, what questions? The origin of the universe, some kind of woo about all that kind of crap. The philosophy ended with Darwin, frankly. I mean, the philosophy, any kind of arguments about, what the hell's going on here, was kind of over. It's a bunch of biological machines. And then if you know any of the physics, the biological machines are programmed. I mean, they don't have there's no options here. There's no spontaneous ideas. Every idea has a cause and effect chain that creates it. Every human has a lineage. Everything has a history. There's no way to evade it. You're just a byproduct of a coalescing of events, and you become the event demanded by the coalition. The events that happened created you, and that's it. You didn't. You weren't going to steer yourself anywhere else. So philosophy's over. There's no philosophy anymore. There's just a definition of the mechanical systems that are dictating your robotic function.
Some of the proposed solutions just are not going to work. I think that philosophers are better at telling physicists where they're not making sense than they are at proposing better theories. So I suspect, I'm happy to get good ideas from it.
Oh, so you're not happy to get good ideas from anybody, so none of that can happen. There's no mechanism for it. You haven't created any mechanism for it. You have this obtuse, silly publishing thing where even if you compose the argument, if you make some kind of error in how the document is formatted, you'll sit there and pretend, oh, we can't read it or something. I mean, it's ridiculous. You're not looking for the truth. You're trying to create a hierarchy of hoops to prevent any truth but your truth getting through, and that's it. There's nothing else going on here. You're just propagandists, and you take advantage wherever possible in closing out any argument that might counter your bullshit.
Anywhere, but I suspect the better theories are ultimately going to come from physicists because that's what they're.
Yeah, yeah. And again, what's the definition of a physicist? Well, I mean, obviously, it has to come from somebody who's analyzed an awful lot of experiments and understands mechanically what's possible, what's not, what the degrees of freedom are in terms of trying to make a calculation. So you could argue that they dismissed particle gravity because they rationally deduced there would be drag as something moved through the universe. But they didn't think about that at all. I mean, in the electron and proton age, once you've established the existence of electrons and protons, it's pretty easy to figure out that electrons and protons do in fact stop. They don't in fact go forever. They do in fact incur something called drag. And so now you just have to explain why helium nucleuses overcome that effect, because elementally it does in fact exist.
Really trained to do.
So, I mean, their argument was wrong. Drag isn't some unsurmountable obstacle because you can already prove its existence.
Philosophers can help them understand why this is just not up to the task when they don't quite do the right job.
So, Stephen.
So that was a mile of mush, right? Didn't say anything there. Whatever the philosophers are doing versus what the physicists are doing, and the whole thing comes down to, can you show me anything? So if I ask them to show me a quark, they're not going to show me a quark. They're going to show me some experiment where they put some kind of force through some sort of, plasma of electrons, and they deflect it a certain way, and therefore we're supposed to deduce, plasma of protons, sorry, that, because the electrons deflected a certain way, the protons aren't protons, they're made out of quarky things. I mean, it's not going to be anything called a proof or evidence or anything. They're just making a deduction that there's hobgoblins that made something happen. They're just making up another bent space story, another dark matter story. Quarks are just the same thing as all the rest of these made-up stories. Up, down, strange, that's physics? No, that's silly.
Hawking is, well known for having a distaste for philosophy, and he wrote that philosophy is dead. And then there are others like Neil deGrasse Tyson or Lawrence Krauss, who I spoke to recently, and I could tell was kind of irritated by my philosophical questions, who have these very negative feelings about philosophy. Do you have any sense of just why so many physicists, and maybe I'm generalizing too much by saying so.
I mean, this is so bizarre because they're not really talking about any subject here. And so how can you make this distinction? All this is one project. Science is to extract formalization statements that are true, like laws, like Newton's laws. All you're trying to do is accurately describe the reality. Now, I could argue that Newton's laws, they're good, but they could be better in the sense that I don't think the third law really gets to the point. That when I give away if I have $10 and I give away $5, I don't need an equal and opposite reaction to take my money away. I already gave it away. So when I gave it away, there's no opposite reaction that makes me $5 poorer. That was built into the fact that I gave the $5 away. So it implies that there's some countering mechanism, just like they talk about friction as if it's a force acting on something. When it's not a force acting on something, it's a sink pulling something. It's taking the energy. You're making something else move. You're giving your energy to something. There's no force fighting anything. It's just nonsense. You're banging into stuff and giving it momentum. You're giving your momentum away. It shouldn't be understood any other way. So I'm just saying, if that's not fucking physics? Yeah, of course, that's a physics argument. You're going to argue it's a philosophical argument? It's not a philosophical argument. So philosophy is about, the stuff we can't physically talk about. So consciousness is a philosophy conversation in a lot of ways. Our value is the most obvious one would be value, because you're never going to make physical value. Okay, you can only have some machine that produces it. You can say, here's a clump of brain and it's producing a sensation, and that I would argue is value. But there's no way for you to see the value in the mechanism that created it.
many physicists are so hostile to philosophy. And before you answer, I mean, one thing that I took from my conversation with Lawrence is that he thinks philosophers spend way too much time worried about quantum mechanics and these debates of the 20s and 30s as opposed to quantum field theory.
Oh, well, I said this is just too ridiculous. I mean, quantum field theory is, I mean, what? It's how much better than string theory is at actually doing anything. I mean, there's no evidence that it's actually accomplishing any task. So why is this a conversation at all? Why would anybody pay any attention to it at all? Because it doesn't answer any questions. It doesn't create any simulation. It doesn't explain anything. It doesn't work. So why bother? Why waste my time with an argument about I should pay attention to the Catholics or I should pay attention to the Protestants, when I shouldn't pay attention to any of that shit? I should pay attention to Darwin.
Yeah, I sorry, what was the first part of that question? You added an extra question on there.
Yes. Why do you think that so many physicists are hostile to philosophers of physics or philosophy?
Well, I think that physicists are hostile to anything that isn't physics more often than...
Yeah. That's just science. It's all science. It doesn't matter. You want to call it philosophy because the subject is a little harder to see with mechanical objects? Fine. But it's really all just a description of the electrons and protons and the force manipulating them. And the fact is, that simple mechanism, electrons, protons, and force, does create brains. It does create very complex things. And those complex things have functions and features that are a little way too abstract to sit there and say, I'm going to have a scientific conversation about it in the sense that I'm going to measure it with a ruler. You're not going to measure it with a ruler. You're not going to measure, how much pain is worth what little gain with a ruler.
Not, the philosophers should not feel picked on. We physicists will pick on economists and historians and sociologists just as well. Don't feel bad, or even mathematicians. Mathematicians get some grudging respect because they're useful to physics. But
so again, how are they useful? In the sense that these bizarre formalization. What's useful is the 2,000-year-old Pythagorean theory. That's really useful. The Roman arch, lots of things are useful in terms of understanding those mechanical systems, and those are the ones that endure over time, and all this woo and bullshit doesn't. Again, the people who are doing, the GPS stuff, they don't do Einstein's equation. They just turn the clocks and make the match. They don't bother. They don't bother worrying about some formalization that'll tell me exactly how much it's off, and the fact is it doesn't tell them exactly how much it's off. That's why they don't bother, because the math is so it's so clunky that it's not going to get you the right answer, and you can just do the calculation and turn the clock. No, it's not going to work.
They're largely wasting their time proving things from the point of view of the physicist. So
you're proving that their math is circular, okay, and that they can create a fake notion, MGH, and we can confirm, F equals, E equals F times D, or some such bullshit when it's F times T.
Again, relentlessly practical. Show me the money. And I'm not.
So, and there's no money here, right? The only money's going to the wooiest crap you can imagine. And some of it only because it has military applications. So they spend some money on fusion because, that certainly has some military applications. And they spend the money on the stupid gravitational waves because, we can use this as a listening device, and maybe we can tell when somebody's testing a nuke or something. So it's all corrupt. It doesn't have anything to do with science and what needs to be proven and what needs to be demonstrated and what evidence you're missing. So they haven't dropped 4 pounds 1 foot and 1 pound 4 feet. No experiment, no paper written on the results of that frickin' experiment. They haven't tied a 10-mass cart going 5 to a 5-mass cart going 10 and see which one wins the tug of war. They haven't done anything to prove this crap.
Saying my point of view here now, but you asked why do most physicists think this way? What's it going to get me? For most physics questions, philosophy has no special way of helping, right? If I want to do an integral, If I want to figure out how to evaluate a Feynman diagram, I do.
Right, so they're saying Feynman diagrams and integrals are physics. When no, that's math, okay? And it's, again, obtuse, and it's dependent on you believing their fable. So if you don't believe you can borrow energy from the future, okay, I mean, that's Feynman diagrams are saying you can do these kind of things, and use it now and then pay it back later in the future, bullshit. If you don't believe that a photon, a complete photon, can be produced by a single electron, then the Feynman diagram is bullshit.
Not turn to a philosopher. The questions where philosophy is very helpful, things like the measurement problem in quantum mechanics, the origin of the universe, questions of net.
Oh, see, none of this is, and again, there's the evidence you're going to be able to compile for any of this crap is so minimal and loose and foggy and fudgy that it's a useless conversation.
Naturalness and fine-tuning and so forth. These are exactly the questions that physicists are kind of awkward about. They kind of get nervous talking about them because they don't know how to answer them. They don't know what experiment to do to figure out what the answer is. So there's sort of a...
So again, for him to talk about experiments when they haven't done any, the only experiments they do are accelerator experiments because it just creates woo on top of woo on top of woo on top of woo because it's all a bunch of fake, phony energy because of that stupid MV squared nonsense.
Mismatch in style, and they can both get along perfectly fine without each other in their own minds. So until philosophy tells physics something that is really, really useful to physics, then physicists are just not going to pay a lot of attention.
Is, quote unquote, solving the measurement problem particularly relevant to quantum field theory or the standard model of particle physics?
So again, and they don't even define what this measurement problem is, in the sense that they think the measurement problem is that the measurer is the problem, when no, the problem is that there's no way for a particle, anything in the universe, not to be constantly measured. It can't go anywhere without interacting with the universe because the universe is so densely packed with crap. All right, your cell phone calls, all the stuff, it's all there. It's all flying through the space. There's no way anything travels without banging into it constantly.
As it is empirically used or empirically confirmed, or something like quantum gravity, because, I mean, as I said, Lawrence...
Why would they even have this conversation about this minutia about philosophy versus physics? I can't even understand what the fucking point of it is. Obviously, there's a philosophical implication to the physics. So if I prove that there's just electrons and just protons and there's just force interacting with them, and they can only be, by simple rules, it's absorbed, it's reflected, or it's changed, and that's it. By very simple rules, very exact, all straight lines, not a single curve anywhere, then yeah, you're stuck with the philosophical implication that everything's determined. There's no way to get around it because there's no loose part. There's no gap for any kind of new thing to happen. And everything, if you can have enough information, you've got the answer. And that's this old, it goes all the way back to people like Descartes. In terms of defining this problem, that there's no room for an action that doesn't have a previous action. That everything is just a cause and an effect, and you can't evade the effect, even if it's 1 billion years from now. It's unavoidable.
Krauss seems to think that no one cares about this but philosophers, and for good reason. And I talked to...
And then the philosophy part comes in where you understand that, well, that doesn't mean we can't see something starting to happen. We can't see a fire on a little bush and recognize that that little bush fire could turn into a forest fire. And then I can just pour a bucket of water on the little bush and I prevented the forest fire. So yes, it's inevitable that I was going to get the bucket of water and dump it on the tree and stop the forest fire. But you're going to understand that, yes, if I didn't have a brain and I wasn't there, that the forest fire would have happened. So you can understand that we change the world, but we change it by reading a script where we change the world. The world doesn't change by itself. We have to change it. People have to go to the war to win the war. They can't win the war unless they go to the war.
Eric Verlinde about string theory, and he seemed to echo this. He just wasn't at all interested in the interpretations. But then other people working on quantum gravity.
So it's just all these ambiguous things. They talk about this ambiguous quantum gravity theory thing. Well, where do I go find the video on quantum gravity? Where do I find any explanation of what the fuck that actually means as a concept? Because I can't find it. I can't find any explanation of what the fuck they're talking about. What the hell is a quantum gravity? And how the fuck does it actually explain gravity?
Like Faye Dowker says that the path integral is quite vital to the program of causal set theory.
The path integral is something the set theory. I mean, this is just jargon. Does that really mean something somewhere? Does that actually have something to do with I kick a ball and it goes? No, it doesn't have anything to do with anything physical or real.
Yeah, I think that our mutual friend Dan Dennett, who passed away recently, has said things along the same lines as...
So Daniel Dennett is a wooicist, okay? He's a guy who can't handle the truth and says, well, we got to figure out some way to fudge it. So he's a normalization. So you can compare him to a normalist in physics. The normalists in physics say, it doesn't matter. Okay, our equation doesn't work in these extreme circumstances. We'll just cut the ends off. So they just cut the ends of the part. They just edit the part of the film they don't like and just throw it in the garbage. So, and that's Daniel Dennett. I'm just going to edit the reality so it feels better. It's a happier story. I'm going to try to shove a silver lining in there somewhere.
What I'm about to say, which is that you can't help but do philosophy when you're doing science. You can only do it well.
No, it's the other way around. You can't help but do physics when you're doing philosophy. Oh, amazing.
Or do it badly, right? There's plenty of physicists who ignore philosophy, but they're constantly making philosophical pronouncements. They're just kind of silly ones. They're not very educated.
Yeah, here's a perfect example. I'll invent some unprovable nonsense about how a new universe is created so I can erase all of the problems the old one created, right? So I got a problem with my when it happens problem, and I can just get rid of the problem because I'll just create some new universe where that circumstance it didn't exist. And so every time something happens that creates some other problem in this universe, I just make a new universe where I don't have the problem. I mean, it's too ridiculous.
Ones, not very thoughtful ones. Again, that's fine for a lot of areas of physics. For quantum field theory, when you want to predict the electric dipole moment of the muon or something.
So again, how does that, what exactly does that have to do with gravity and all this? No, it doesn't have nothing. So this quantum field bullshit doesn't really explain anything. And again, their muon experiment already played, from the 50s. I mean, it has these huge gaps in logic and reasoning in terms of they're using the same sensor to detect the incoming event and then the decay event. And there's no distinction. They're both photons. One creates photons, the other one creates photons. The signal says photon. There's no way they're detecting anything
like that. Why in the world do you need to think about philosophy to do that? But on the other hand, quantum gravity, emergent space-time, things like that, these are precisely areas where philosophy might be super-duper important.
Super-duper again.
Cosmology overall, with things like the anthropic principle. The anthropic...
So again, the anthropic principle based on absolute, just incredible ignorance of the fact that gravity is creating energy. That gravity is heating. Every single big object in space is getting really, really hot because of gravity. And they're going to talk about how we have a heat problem. We're going to run out of heat. How are you going to run out of it when you have a bent space creating essentially free heat because you don't have any explanation how the bent space reabsorbs the heat? So you have exactly the opposite problem. You have a constant source of new heat in the universe. The exact opposite of an entropy problem.
principle as deployed by many physicists is exactly an example of philosophy done badly because they haven't really thought these issues through. So I think it just depends on what you're interested in. If you're a physicist who doesn't like philosophy and you stay away from those questions.
I can't even imagine how you would mix the two subjects other than for no good reason. I mean, if the physics really is, well, let's go look at the experiment where they drop 4 pounds 1 foot and 1 pound 4 feet. Let's analyze, well, what actually happens. How many seconds does it take for something to go 4 times the distance in gravity? Oh, it only takes 2. So it goes 4 times the distance, but it only took 2 seconds in the gravity. So the gravity could only act on it for 2 seconds, and it's 9.8 meters per 1 second. So 2 seconds would be 19.6, and that's exactly what we get. That's physics. That's not what they're doing. So obviously they're not doing physics.
In areas where philosophy is important, I think you can be fine.
While we're on the topic,
See, their philosophy is that, oh, okay, we don't have to obey the speed limit. We can create wormholes. We can, well, these black holes are singularities where all the matter is somehow in the same location in space. Space isn't really some kind of stuff that prohibits that kind of crap. Like matter can't actually occupy the same exact space. That someday I can build a little device and I'll be able to, whatever it is, be just like John Malkovich or whatever that movie was. I can live inside of somebody else. Oh, too pathetic. It's all daydreamy, wishful thinking crap. It's all sci-fi nonsense.
Topic of use and understanding in regard to physics, and before we actually turn to some of the physics in the form of quantum fields, I wanted to talk a bit about scientific realism. And for our listeners,
brother, so all this, what is this? Scientific realism, as opposed to scientific fakeism. Oh, okay. Yeah, let's do the real part.
Who aren't familiar with this debate, it's one of the biggest debates or topics in the philosophy of science. It's the question of whether we ought to be committed to the existence of the objects or structures postulated by our best scientific theories and historical.
So again, there's just no evidence of this, like somehow it's wooey. So again, the quarks only exist when you blow the protons up, okay? And there's no evidence that in that high impact circumstance that you're really making pieces. You're just making bits of energy fly off, and then you're calling the bits of energy a proton or a positron or some other bullshit. Okay, because that's all you get is a little bit of impact. You don't know whether it's a force that hit, you don't know whether it's a particle that hit, you don't know what the fuck happened. So again, it's all just made up bullshit. And again, so these things only exist in some circumstance that is very improbable, and yet somehow this is an important subject. Of course, it's not an important subject. It has no importance at all. It doesn't mean a damn thing. Quarks are not quarks most of the time. Most of the time, quarks are protons. 99.999999999% of a quark's life is going to be, I'm a proton. It's not going to be, I'm a quark.
Historically, I think, and maybe you can weigh in on this, but the strongest argument for having commitments of this sort goes back to Hillary Putnam and is called the
the cat saying, what? What are you talking about? Could you speak English?
no miracles argument, and it holds that it would have to be some sort of miracle for the predictions of, say, the standard model of particle physics to be observed to the degree of accuracy that they are without this.
All right, so again, they keep saying that there was some degree of accuracy predicted by the standard model doing something, and there's no way to find any evidence of this miraculous predictive power. They just keep saying we have a device, okay, that we built that does a specific thing, and we predict that it comes out this way, and we can add more and more .00s because we're measuring it more and more accurately. Each time we measure it, we do it a little better. The ruler's a little bit, the number lines are a little bit finer. We make a little tiny bit better ruler, so we get a little bit better number. And we're just measuring something we created to be measured. It's so circular. It's just nonsense to say it predicts something. It doesn't predict anything. It's just such hype.
standard particle model being at least largely true. But then, on the other hand, the best argument against it is known as the pessimistic meta-induction, which holds that basically if all of our best theories have been false in the past and we've had to throw out those either object-based or structure-based ontologies.
Look, they didn't even bother fixing something as critically important as getting plus and minus assigned reasonably. That is, that you can only add electrons, so to speak, okay? And so electrons have to be the positive element and the proton has to be the negative element, because all of the electricity formulations break down if you don't do that. And you end up with this ludicrous circumstance where they say the amperage, the mass, okay, in the wire is going this way, and somehow the voltage, the pressure, is going that way. I mean, it's stupid to keep something broken. And I would argue that mv squared is obviously crap. It doesn't have any credibility. There's no evidence supporting it. And yet, 300 years later, you still haven't figured out that you shouldn't have something in your foundation that's completely unevidenced fable. So, of course, it's going to, if I'm right, and I'm quite certain I'm right, it's going to blow up so much of their physics, because all of their physics, like I said, they measured the weight of an electron based on this idiotic formula. I mean, it's going to come down to is that, you know what, there might be a someday where the atomic number, your atomic weight, is going to be your real weight. The two are going to match perfectly, because that really is all you're made out of, is electrons and protons. The neutron is an electron and a proton.
Is it rational to have any credence that our current ontology is right? So, in general, where do you see yourself in this debate as it relates to quantum mechanics, or maybe more particularly the standard model?
This is the premium garment duffel.
Oh, god damn. Anyway, yeah, okay, I'll pause this time, try to do it right. All right, so Sean Carroll says, I think that...
There's two separate questions. One is, within the way that we think about any one theory, does the best way of thinking about that theory hold that you should treat certain parts of it as real? In other words, specifically what I have in mind is, in quantum mechanics, do you treat the wave function as representing reality? Some versions of the foundations of quantum mechanics say yes, some say no. That's just purely within everyone agrees on quantum mechanics, right? But we're disagreeing with what parts of it are ontologically relevant. There's another question. I think it's a separate question.
I mean, it's just so bullshit. Oh, we have something that's an inaccurate construction, but it somehow gets right answers. And that's the bullshit here. Because it really doesn't get right answers. They just say it does. They never tested the answers.
Question to ask, okay, but you don't know that quantum mechanics is right? I mean, that's the question about meta-induction. And you might say, well, why bother thinking that wave functions are real if someday wave functions might disappear because quantum mechanics is no longer right? And for the latter question, I think that structural realism essentially solves it for me. The idea that what is real and what is not going to go away are certain patterns, certain structures in our theories that have been empirically verified.
So I don't know what those would be. So again, he would say that 1/2 mv squared has been empirically verified. No, it hasn't. So that's the simple accusation, is that anything he claims to be empirically verified, the existence of space-time, empirically verified, well, no, it really hasn't. The Eddington experiment's garbage. And everything else is just based on some sort of supposition, some axiom that states that atomic clocks can't be broken.
Newtonian mechanics has a different ontology than general relativity does. But apples still fall from trees in both Newtonian mechanics and general relativity. So it's okay to attribute some reality to that phenomenon, even though the ontological explanation for it is completely different in these two.
So it does matter, though. So again, it's all about the right inverse square law is the basic law. So that's the difference, right? So Newton could say, okay, he believed in particle gravity for a while. I mean, he thought particle gravity was a good idea. Let's just say that. A viable theory for a while. And he never discounted it as impossible. And he clearly made the statement, you'd have to be an idiot to think there isn't a mechanism. Okay, there's something causing it. Okay, you're giving things momentum. Something has to be giving them the momentum. They don't just poof. It doesn't just poof into the object to start having momentum in a direction. So, I mean, Newton was smart enough to figure that out. But this whole idea that you can have the wrong idea and still get the right answer. Yes, so you can have a wrong idea. That is, you can draw your bent space as a well, or you could draw your bent space as straight lines, right? So you can do different ways of drawing it. And frankly, I'd say one drawing is a lot better than the other drawing, but the drawings don't have to be exactly alike, and you'll get the same impression or the same understanding of the fucking idea that the thing falls into the center. It goes to the center. But it really matters. Getting the right answer is the whole point. Not, making wrong answers work is not the point. The point is to find the truth.
Two different theories. I don't think anyone should claim to know the final ontology of nature and only be realistic about that. That would be very, very hard to pull off.
It says you. So there's some things we know for certain. There's certain things we can't, we even have, computer models that can pretty well predict what a hurricane's going to do, pretty accurately. So it's idiotic to say that we don't have good reason to be certain about a lot of things.
But you can think that there is something that is the final ontology, even though you don't know what it is. And these structures that emerge at higher levels are what we are learning about through scientific practice.
So the structure at higher levels, whatever that even means, what's a higher level? And for them, the higher level means we're going to find some little particle that has ESP. We're going to find some little elemental functioner in the universe that has these special qualities, some kind of gluon thing, that can shoot its tongue out and grab a proton and then pull it back towards itself. Some kind of bullshit fabulistic hobgoblin to perform certain tasks necessary for us to understand why we get diseases or something. We're going to blame it on, Smurfs. Smurfs will never be the right answer.
Now, in the question of quantum mechanics itself and the wave function, I agree with Putnam. The wave function is super duper useful.
Super duper useful. In what? So again, show me where the wave function does something. Show me where you actually do this equation and figure out what the roulette wheel is going to do, or some other probabilistic system. Show me how this thing is at all useful.
Quantum mechanics, we really can't do without either it or some equivalent of it. So, of course, I think it's just very...
So, everybody can do without it. The bridge engineer, anybody doing anything, the rocket scientist, they can all do without it. Because it doesn't do anything. Because it requires you to know everything, and you can't know everything. So it's useless.
Natural to treat it as representing part of reality. And it's a short road from there to believing in the many worlds interpretation of quantum mechanics.
Oh, there you go. It's a short road to believing in some silly woo about how we make new universes to get out of our trouble. So, there's somebody tied on the railroad tracks. Oh, dear, what a problem. The train's coming. What do we do? Let's just make a new universe and escape the problem altogether. It's just such bullshit.
We can argue about that. But I'll point out that in the book, this came front and center, even though my goal was to only talk about things everyone agrees on. I had to talk about quantum mechanics, and not everyone agrees on quantum mechanics, even though they agree with the final predictions.
I don't even know how the book has anything to do with anything. I've watched his videos, and the videos are all this abstract crap. So how could there be anything in the book that wasn't subject to some disagreement? Because none of this crap, is evidenced crap.
But the way that you talk about it along the way can be very, very different from person to person. So I made an executive decision saying I'm going to talk about quantum mechanics as if the wave function is real. And if you don't like it, you can always translate it into your own way of thinking about it. But I can't, every time I try to say something about virtual particles, include 2 pages of disclaimers and caveats.
Yeah, so exactly. So why even entertain such a silly notion as a virtual anything in the universe. Isn't that just saying hobgoblin? Invisible little mechanism that does something, but yes, we haven't figured out what it is, so we'll just call it virtual something. I mean, it's just such bullshit.
Saying, well, different people will talk about them differently.
This is a good point for us to get into some of the physics, just to make...
Thank you, finally. Yeah, let's hear something that has something to do with physics. Actual physical objects interacting in the universe. I'd love to hear some of that.
Sure that our audience has a grasp on what we're talking about going forward. And I know that this is very basic, especially since we've been referring to it for the last 5 or 10 minutes, but restricting ourselves to...
They were referring to something for the last 10 minutes that was real? Oh, I don't think so.
Quantum mechanics and not yet going into quantum field theory, though I know that that is part of quantum mechanics. Just what basically is the wave function?
Good. That might as well start there, I think. That's chapter 1 of the book, the wave function. And I think that it's a profound change in how we think about the world that happened.
So it's nothing good comes of this. And even the guy who invented it says, you've perverted it into crap I didn't. That's not what I was saying it was. So they, just like Einstein, just like they took Einstein's theory and bent it and perverted it into something he couldn't recognize, you know, black holes and singularities and all that crap, they did the same thing to Schrodinger.
And starting in the year 1900, but you know, the revolution was completed in the 1920s. And the simplest way to skip over all the missteps along the way is to say, when we had classical mechanics pre-1900, if you were Isaac Newton, you would say, if I have a collection of particles, for example, I can talk about the state of those particles, the physical state, and that physical state is defined as the information that I need to know what the particles are going to do in the future and to know what they did do in the past, right? I need the positions of those particles, and I need the velocities, or equivalently the momenta of those particles. And then the laws of physics, if I know what kinds of particles I'm talking about, so I know their electrical charges and masses and things like that, the laws of physics tell me how they develop over time. And quantum mechanics comes along and says it's radically different than that. Like this.
Okay, so yes, and that's the big distinction. So I mean, I have a simulation, right? Now the simulation always starts with conditions different. But I mean, theoretically, I could start the simulation with exactly the same conditions, and you could just watch some very complex thing just happen each time, because the forces will all be going the same speed, the material elements are going to start in the same position, the rules that govern how they behave are strict, so every single time I ran the simulation it would do exactly the same thing, and all I have to do is change one of the 10,000 bits of force. So I just take one of the 10,000 bits of force out and I change how it evolves. And that's the interesting part, that all you need is just one little piece of elemental bit. All I have to do is change one little tiny piece, and the whole thing now reaches a different destiny. And that's the physical universe. That's how it works. And it's so precise that we can't change anything. We can't change one single frickin' grain of it in any way beyond, you know, us actually physically doing something, blah, 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 that requires us to actually interact and do the event. There's no other way for the change to happen than us to be part of the change. And so, yeah, that's physics. And this wooey crap that somehow it's all doesn't know what it's doing and it's not in any kind of condition, and that somehow you can change the outcome by doing something on the outside to change the outcome. It's just such bullshit. You can look at it and change the outcome. No, you can't do it that way.
It's amazing how different quantum mechanics really is. And this is part of the reason why even physicists have trouble facing up to what quantum mechanics says. It says, for one thing, if I just have one particle, I don't have a position and a momentum for that particle. I have this thing called the wave function. And the wave function can be expressed in different ways, but it's easiest to think of it as literally a function of position. So everywhere the particle might have possibly been, there is a value for the wave function. In a typical situation where like the particle we're talking about is an electron in a hydrogen atom, and you have a picture in your mind of the orbital.
Look, this just goes back to their wave nonsense. So their idea is they think everything is waving, so that it's going to all locations. So the energy of something, there's a something here, and it's technically got a component that's going in all possible directions. And that somehow, because it's going to get de-entangled or it's going to interact with some kind of other substance, that now it's going to retract all of that, all the energy, all the stuff that it was doing. It was going everywhere, and now it's just going to go to one place. It's that kind of silly. And there's just no reason to believe any of that. No reason to believe that these small objects are doing any of this magical stuff. And the only way they get away with it is because, yes, it's a very small universe and we can't take a picture. And so because we can't video it, they can give it all kinds of wooey properties. They can say that this electron is in more than one place. They can say it's all kinds of bullshit because we can't photograph it. And so they're just getting away with it because it's the smaller verse and they can make up any kind of crap they want to. But they wouldn't get away with it in this real universe because we don't see anything like that. Nothing, ever. There's no such thing as a real ghost. There's no such thing as a real mirage. There's no such thing as a real optical illusion or any of that crap. It can all be physically understood as vectors and rigid physical mechanisms. No woo necessary.
Of the electron in the hydrogen atom, that orbital sort of stretches out to infinity in principle. It fades away, but very, very, very quickly actually, but never quite gets to zero. And that represents the wave function. That is a picture.
Yes, this moronic picture that somehow there's all this capacity for it to do things that there's absolutely no evidence it did or will do. And just make it up.
Picture of the wave function of the electron. And
so, I mean, this, like I said, this can sort of be seen in experiments like the double slit, where they don't bother putting the photographic film on the two sides and see if any of the photonic energy, the fringe pattern, shows up over there. Because if the wave theory had any credibility, they should be able to detect photons over there. And they've never even tried.
I forget if I said two things, but there's really three amazing things going on here. So the ontology is completely changed. Number one, you went from a particle with position and velocity to a cloud, right? A wave, a function of space, the wave function.
So why would you believe? Why would you say you have any good reason or any good evidence to believe that the elemental particles, especially when you know something like photons travel hundreds of billions of light years through space, well, billions of light years through space, and they very precisely hit places. I mean, with insane precision, insane reliability. Why would you think that they're all amorphous and blah, blah, blah? Why?
Number two, you can never see the wave function. We're going to get to that when we talk about measurements, but when you look at it, you don't see it. And that's why it's legit to worry about whether the wave function is real. Why are you demanding reality to something that I can never even see? That seems a little bit fishy. But then third...
It's not fishy, it's dead ratty.
When you have two particles, you do not have two wave functions. If you did have two wave functions, that would be saying I have the Greek letter psi is the variable usually used for these kinds of things. So psi of x would be the wave function of a single particle. If you thought that when you had two particles, you had two wave functions, you might imagine having psi 1 of x, which is the wave function for particle 1, and psi 2 of x, which is the wave function for particle 2. But quantum mechanics says, no, that is not what you have. You have one wave function as a function of two variables, the two possible places I could observe, particle 1 and particle 2. So instead of psi of x for one particle, for two particles I have psi of x1 comma x2. So it's not even a wave, it's not even a field in the usual sense, like the electromagnetic field or the gravitational field. These are fields. They have values at every location in space. The wave function does not have location values at every locations in space.
So there's even this rhetoric of values in every location in space doesn't mean anything if it can't produce anything called action or motion. So clearly, if you're going to say, yes, I could sit there and I could show you a diagram of photon, right? I could say when the photons are close to the sun, they have a high value because you're going to get hit with a lot of them. And when the photons are further away, their value goes down, way down, way down. Or it can make them get smaller and smaller and smaller. And illustrate the inverse square law, the fact that they're spreading in 2 dimensions and their distance from each other is getting greater and greater and their capacity to hit you is getting less and less. What is that? What do I need a wave function for? Oh, that's right. Don't need it.
It has values at every possible set of observational outcomes. If I were to look for the 2 particles, then I would be able to see the probability that they're here and there in different places. That's what the wave function tells me. So it's a very abstract, very completely different thing, and that's why physicists are still struggling to come to terms with it.
Because it's nonsense. Yeah.
You have said about 20 things that I could ask questions about, but I will start with one thing that you said a few minutes ago, I mean, even before this response.
Hilarious. So he asked him to define the wave function, and then he says, well, let's not talk about that.
You questioned whether we should think of the wave function as representing reality. And I think there's a deeper question here. I mean, one, what it means to represent reality, or versus the wave function.
This space heater is being called the Tesla of heaters. It can warm up houses for practically zero cost.
Just amazing, the low quality of commercial advertisements on YouTube. I mean, they're all rackets and shit. Just there's not like one legitimate product I ever see advertised on YouTube. It's never, it's all these fake cure your cancer crap, all kinds of fake. Amazing garbage.
Reality. And you also said that you can never see the wave function. So one, a function, at least mathematically construed, is just a set. It's typically thought of as a set. But then on the other hand,
hit the wrong button. I mean, it's just so irritating for him to say something like a function isn't, that's math, and the function doesn't have to have a real mechanism causing the function. So there's no such thing as a function. I can't have any functions that aren't physical, real things, right? I got no functions. If I see because I have eyes. If I smell, it's, because I got the mucous membranes or whatever and tongues. If I do, I have to have real mechanisms to have functions. I can't have a function without a mechanism. A battleship can't shoot shells at the shoreline unless it has cannons. I mean, it's just so annoying that they say, oh, just create a mathematical abstraction, and that's the same thing as defining the mechanism that causes a function. Oh, bullshit it does. Bullshit that's good enough. No, it isn't.
Lyman here at Stanford, who was the first person to isolate a Bose-Einstein condensate. And he said that the way that he described it is when you have this Bose-Einstein condensate, you are looking at a wave function. That is how he describes it. So the question I have, I guess, is whether the wave function is meant to be something that represents reality.
So too bad we don't have a video of that, the Bose-Einstein condensate, and so we can see what a wave function looks like.
Or is it something that is real itself that you can observe?
I'll be honest, I don't think this is a very sensible question to ask. I know why people are tempted to ask it. Is the wave function real, or does it represent reality? I don't know what the difference is between those two things. Like, it's a function. What does it mean to be real,
Mechanism, that's what it means. It means hobgoblin versus stick. Hobgoblin, different.
Like, it's the mathematical way we describe reality, by which what we mean is if you set up reality in a certain way and you let reality go, then you make a prediction for what you're going to observe.
And you will not do any of that in any kind of clinical way that you could show somebody how you predicted the outcome. None of that will happen.
Can construct that prediction by setting up a certain mathematical fact, the value of the wave function at different points in space. I can evolve.
I mean, without us already knowing, like there's six, there's the faces on a dice, and you roll the dice, right? And you can figure out, oh, okay, yeah, there's 6 sides of the dice. Okay, I can figure out the odds of this number of combinations, But you can all predict that. Let them predict something that isn't where you don't know the answer because it's already written in the variables we know. We can see the variables, and therefore we can know the outcome. Do it when we can't see the variables.
Solve it using a certain equation, and then I can do a certain procedure to it to make a prediction. But reality is reality. Reality is not some mathematical thing we invented. Reality is sui generis. It's uniquely reality.
Oh, please, uniquely reality. So either the universe is made out of objects, real things, not nothings, somethings. There, that's the word. The universe is made out of somethings, and the somethings have do something properties. Okay, it's either that universe or this wooey mush-averse of whatever the hell the forky thing is. The wave function.
The scientific question is, how do we model reality? How do we describe it? What is the language that we use to talk about it and make predictions? And to me, the wave function is part of that. As far as seeing the wave...
there just won't be anything. There won't be a simulation of this wave function. There won't be anything.
Function, we can't do it. I think that Carl Wyman was just exaggerating a little bit for poetic purposes there. Of course... this is a problem due to the fact that physicists don't agree on what wave functions are or how they should be talked about in a very real way. In anyone's version of quantum mechanics, when you have a physical setup described by a wave function and you're going to make an observation, in the general case, sometimes you get lucky, but in the general case, the possible measurement outcomes do not include, here's what the wave function is. They include certain aspects of the wave function, and they might include different aspects that assign different probabilities to them.
Oh, brother. It's just, So this arbitrary gibberish has something to do with reality. Let's qualify it and say, well, it doesn't work, and it isn't this, and, it could be a little bit of that, and there's some of that in there. There's some that in there and some that.
That's the fact of measurement in quantum mechanics.
I mean, this is like, and there's a sprinkle of love in the cookies. Grandma sprinkled some love into the cookies.
Is that measurement changes the quantum wave function. That's not true in classical mechanics. You might think, well, in classical mechanics...
classical mechanics always says, yes, pretty much, there's no way you can interact with something within some way changing it. Now, whether you're going to change it dramatically or not, okay, obviously I could throw, a pea at a Mack truck, and I'm not going to change anything that truck's going to do that day, okay? It really isn't going to change anything. But obviously we're talking about subatomic particles, and in that universe, any kind of little tiny change is going to make a huge change. It's all a quantum of change, and all you need is one quantum of change to change everything.
Mechanics, if I want to take a picture of a planet, I need to observe the photons.
I mean, there's a high probability that if, you change who you're married to, that you've changed who a lot of other people are going to be married to. Just a fact. So it depends on the system, how much what quantum you're changing. And obviously, like I said, in an electron system, the little quantums matter. In big systems, throwing a quantum at the truck ain't going to make a difference in the truck's behavior.
Coming off of it, and so some momentum is leaving the planet. But come on, you can make that exchange of momentum as tiny as you want. You can observe things in classical mechanics.
So I don't even know how you make that even make sense. Momentum is a measurable quantity. How can you change it? It just doesn't make any sense.
As close as you want to not disturbing them at all. Whereas in quantum mechanics, no matter how hard you try, certain kinds of measurements are always going to disturb the system by a lot.
Okay, and that's true in the classical sense. If I crash a Volkswagen into a Volkswagen to see where the Volkswagen is, obviously the Volkswagen is not going to be where it's going. It's going to be somewhere else because I crashed a Volkswagen into it. So again, it's just a lie to say there's nothing I can hit anything with in classical physics that's going to make a difference. When of course it's the same rules. It just has to do with how big the thing is I'm hitting and how big the thing I'm hitting it with is. Duh. So this is a distinction without a difference. This is just such bullshit.
That is one of the things that makes quantum mechanics fundamentally different.
Yeah,
I finally got rid of my...
It's obviously not fundamentally different at all. I mean, that's the joke here, right? I mean, there's no fundamental difference between the two systems in terms of understanding that I can throw a piece of dust at a Mack truck and I'm not going to change the truck's destiny for this day or any other day or for the rest of its existence. There's nothing going to change in that event of the truck. Okay, it's not going to be enough of a flutter in the wings of the butterfly to fucking create a hurricane. None of that's going to happen. Okay, so in classical systems, it's the same rules that there is in these fake systems of theirs. It just depends on how big the interaction is. Period. All right, let's get. Okay, well, that's an hour, right? So, yeah, we'll call it there, and I'll figure out where we are in the video and such after I get rid of the fucking ad. Anyway, so that's part 2, and till the next time and such.